Okay, now we're going on to part 3 of this discussion, how light and matter interact. So I have a picture here. We're going to look at it in another context in a little bit. But this is the spectrum of the sun. This is what I call a bar graph picture of the sun. And what I want to discuss with you is not only where all these spots come from. So let's go back to the hydrogen atom. We have a proton and an electron, and it's really, these two pieces are part of the atom, right? And we have the proton in the center. It's 1,000 times smaller than this big billiard ball, and this electron is invisible, right? It's just a cloud. And basically the electron circulates around, the proton in the center. And one of the odd things about atoms is, unlike this picture for the planets going around the sun, there are only specific ways that the electron can orbit the atom. And it's basically most characterized by considering what happens when we are climbing a set of stairs. We cannot climb a half step. We cannot go down a half step. It's always a unity amount. And when we characterize these changes by specific values, we call that quantization. Okay, so the atom, as been observed, can only go into different states that are specifically different from each other. There's no continuum between going from an n=1 state to an n=2 state, for example. Okay, it's like climbing stairs. I can either go up one stair, I can go up no stairs, I can go up 3, I can go up 10, things like that. But I can't go up 1.5 stairs. That just doesn't work. Now, this idea came across. It's called quantum mechanics. And there's all sorts of fun things you can research about quantum mechanics. It can get very mathematically heavy. As you might guess, I kind of like that sort of thing. But there's also some deep philosophical issues about it. And those are sorts of things that you might be interested in. This is something that one of the people I look up to, Richard Feynman, basically said that if you find somebody who claims they understand quantum mechanics, then you know he doesn't understand quantum mechanics. We can do the math. That's pretty much not simple to do, but we can do it. But to understand it is different, and that understanding is kind of hard to come by. All right. Now, a couple things to notice here is we're going to start with a ground state. So this is a state of the atom that is its absolute minimum energy level. Nothing smaller. It can only be bigger. And what we're going to do now is characterize what we mean by absorption, and specifically absorption of light. So here we have a picture, a Bohr atom picture, of the ground state of an atom. And actually we're only showing one electron here and a nucleus, and we're sort of forgetting about all the other protons and all the other electrons in here, okay, in this atom. And what we're going to see is this electron is in its ground state, and in a moment in time it's going to absorb a photon. And this photon is going to cause the atom to get into a more energetic state, and the way we characterize that is that the electron moves out into a larger space. So the atom itself subsumes more volume. Now this photon has to have the right energy. The energy that it has to have, it can be no more or no less than the change in the energy state going from here, from the ground state of the atom to the excited state. Okay, so it's like you have a certain amount of energy that it takes to go up one stair or two stairs. That's it. If you don't have enough energy to go up one star, or you have somebody gives you energy to do 1.5, then you're not going to be able to climb one stair, or you can't climb 1.5 stairs. So that energy is going to go sailing right through you. So if this photon doesn't have enough energy to excite this atom in a quantized fashion, then this photon goes right through. Now, on the other hand, we can, once that atom is in the excited state, then we can emit a photon, and the electron goes, we say, jumps down into a ground state orbital, but basically it's the whole atom changes, right? The whole atom goes to the ground state. Okay, so absorption and emission will be characterized by the same frequency photon. Either the photon is being absorbed, or the photon is going to be emitted from that atom. And here are some pictures of emission spectra. And this is, as I said, emission spectrum. This is somehow we have energized these elements, hydrogen, helium, sodium, and mercury, and they are now relaxing and emitting light. And they will emit it in these characteristic colors. Now, there are other colors that are outside of the visible spectrum, both on the ultraviolet here and the infrared. We can't see those. But we have instruments that can read those things. And you'll notice that there are different colors and different ways that these spectrum appear. I mean, all of these are quite different. And let me show you this video. It's kind of a nice video. It's as you can see, it's burning salts, and you could look this up on YouTube as well. But let me play it for you here. Well, it looks like I can't. So, all right, so here's the flame test.
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with barium ions burning a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally potassium with the purple or lilac shade.
What's really neat, as we change off, is that folks in around the 1850s to the 1870s did this all the time, and that's how they characterized one element being different than the other. And that's how they figured out the periodic table and added more elements to it. Okay, so let's quit this thing and go back to our charts. So this is an example of the stair steps that we would see for hydrogen. And some of these we can see. I believe that's the Balmer series. Some of these are ultraviolet frequencies, which we can't see. Some of them are infrared that we can't see as well. Okay, now where does the light come from? Well, this is my stair step ladder thing again, and we can carry the analogy a little bit further. We can, instead of using ourselves as an example, let's use a pigeon. Okay, so a pigeon, if you give him some energy, maybe he'll climb up a step. But at some point, what that pigeon can do is he can have enough energy and jump up and completely leave the Earth, fly around. Okay, so that's a possibility for atoms as well. You can give enough energy to the atom such that the electron is discharged from the atom, and that's called ionization. All right, so in the beginning of this portion, we talked about the solar spectrum. And this is a different bar graph picture of that, you can see there's going to be a correlation of these lines here, these black lines, and kinks in this, what appears to be a black body spectrum. Okay, so this is called an emission spectrum because it looks like a black body, but it also has these kinks in it. But if I look at it with a spectrometer, for example, the CD spectrometer that is an extra credit opportunity, you'll see these dark lines appearing, and so that's where these kinks are. Now, the next thing I want to talk about is there are 3 different types of spectra: continuous, absorption, and emission. I'm sort of jumping the gun a little bit. And the chart here is supposed to represent a hot black body. So remember what a black body is. A black body is emitting radiation at all different frequencies because of the intrinsic temperature that it has. Okay, so an example of a hot black body is sort of like the sun, mostly, but say an incandescent bulb. Okay, and most of you are not familiar with that, and I hopefully will create a video that will show that, or find a video to present to you. Now this chart, as I said, starts with this black body, and in each one of these cases I have a prism and a bar graph picture. Okay, so here's one, here's another one, and here's the third one. These are all spectrum looking at various aspects of this system. Okay, in this particular case I'm looking just at the naked bare bottom of the black body. Okay, nothing else is getting in the way. The prism will split up the light into its characteristic pieces and create this rainbow. No breaks in it, just continuous rainbow. Now suppose that there is a cooler gas cloud here. Okay, if I look at the cloud, I'm going to see light, and it's going to be dependent upon how I view it. So let's go back to the black body and consider what's going to happen with this cloud. Well, the black body is emitting radiation. This radiation is of all different frequencies, as evidenced by this picture here. And this cloud of cooler gas is going to be energized. Now, it's only going to be energized at particular frequencies, right? If you recall that previous picture that we showed of the spectrum, right? Coming back to here, atoms will only choose to pick out certain energy wavelengths. So if I am producing all sorts of energy wavelengths, only specific ones are going to interact with this and be absorbed. Only certain wavelengths are going to be absorbed. So if I look at this cloud and there's nothing behind it, I'm just looking at the cloud in sort of this direction. That's what this line is supposed to indicate. You know, if I break this line and I continue with it, it misses the black body. So I'm looking at this thing, and it's going to be glowing. And the colors it's going to be producing are the energy, only the specific energy wavelengths of those wavelengths of light that were absorbed by the cloud. Okay? Now, if I look, say, through a telescope, and I see the black body behind it, and this is an example of us looking at the solar atmosphere. So over here I would have the solar atmosphere, and here I'd have the depths of the sun. The sun is producing a black body radiation spectrum, and then it hits the atmosphere, and some of those atmospheric elements are going to absorb the energy and then re-emit it. And when it re-emits that light is going to go off in all sorts of different directions, as evidenced by this picture here. So there's going to be a decrease in the amount of light that's being re-emitted from this cloud in this direction. But the light that is not being absorbed goes straight through. That's why in the regions that are not associated with the elemental content of this gas, I have a continuous spectrum. It looks like this. But in those regions where the element of the cloud is absorbing the energy, I'm going to have fewer photons coming through and striking my detector. Because of the ability of our eyes to see contrast and its limitation of seeing that contrast, I perceive this decrease in the amount of light I see here as a black band. And if I look at the intensity profile, what I see is a kink. The black bands here and these light bands here go hand in hand. This one matches this one matches that one, and on down the line. To give you an idea of the different spectra I can see from the different elements, I want to convince you that all these elements have a different frequency spectrum. There's this applet from the University of Oregon, as you can see here, and I'm really surprised it's working on my computer these days. This is the first time in many years. This little applet allows me to look at the spectrum in the absorption way or the emission way. So let's take a look at the emission way. And we start off with hydrogen, and now we'll go to a different element. Let's say magnesium. That's different. And that's different yet. This is scrantium. Here's titanium. Here's aluminum. Here's silicon. Here's helium. No matter where I go on here, I'm going to see different elements. Oh, that's pretty simple one. For neptunium. Here's uranium. That's way more complex. And oh, here's americanium, and it's only got a couple there. Anyway, the point being is we can that every element is unique and different, and for that reason I can identify elements very, very far away. All I have to do is heat them up, and they will radiate at their characteristic frequencies, which is going to be different for each element, and I can uniquely determine what's going on someplace else. I don't have to be there. So I can look at a spectrum from a star very far away, and if a planet goes with an atmosphere goes in between me and that star, I can figure out if that planet has got life on it, because life emits light at a particular frequency. I would be looking for water vapor, oxygen, ozone, maybe chlorophyll, all sorts of things like that. If I got methane and ozone together, that's a dead giveaway. So those things I can figure out and see from hundreds of light years away. Just amazing. Okay, we can look at stellar spectrum. And this particular chart shows the spectrum from very, very energetic stars, O-type stars, and then very, very dim stars that are very red in color, these M stars. And there's a link here to Ohio State, and you can see that link there. And basically we can you can see what those spectra look like in color. But in the very beginning, I would know that this was 450 nanometers, and that was 750, and then this would be halfway in between, and then I could characterize what these things were without looking at the colors of them. All right, so the next step is this one. Now that you're experts at different types of spectrum, then I would ask you to do this. Take this picture, and there are two pictures here. One is the intensity profile right here, and the other one is the bar graph. So these two should give you enough information to identify the two continuous or thermal spectra, as well as the emission lines and the absorption lines. Now you should be able to do this now. I'll give you the answer. Here is the answer. This is again looking at our picture of Mars, and from the emitted light from Mars, we can discern what's going on. I think this is pretty amazing. We have two thermal spectra, or two continuous spectra, one here and one here. Now, the thermal emission of the sun is really over here, and so you see a big cutout here and here. Still, this is a continuous line. And then we have some spikes here, which should sort of get you to think that these are emission lines. And then I have absorption lines over here. As you can see down here, I have my black bands here and here. So the black bands are at a particular frequency, and it's associated with carbon dioxide. And the emission lines are also at carbon dioxide, but they're emission ones and at much higher energy. So it's very interesting that from just a picture of something, I can discern what is the planet made out of, okay, and what is in its atmosphere. Just totally blows me away. I mean, talking about distant communication, this is what this is really distant communication. All right, so we'll stop here, and the next section will be about Doppler shift.